Song. Song has been a really great student, one of the best students I've had the privilege of supervising in more years than I'd like to admit of being a faculty member. I guess it's actually over 30 now between MIT and Stanford. And he has a bunch of great attributes. He's very broad. He has expertise that ranges from VLSI circuits to computer architecture to artificial intelligence. And by spanning those areas, he's been able to make connections and apply techniques from one area to the others and do very innovative things. He's also really smart. He's come up with a bunch of great insights and has worked on problems that some people have been working on, since the early 90s, and has made unique insights and been able to improve upon previous results because of his unique ability to see things in a different way. He also has a tremendous amount of leadership capability. He acts as a mentor to sort of all of the junior students in my group, and actually to a bunch of people in other students in other people's groups as well, and is very effective in helping students advance and getting them to move along with their research program. And above all, he's just a really great person. He's fun to be around. He's kind. He's very considerate of others, and it's just a real pleasure to be with, whether as a student or in any way. He had sort of a long journey before we arrived at his PhD topic. The theme of my research group is to try to improve the energy efficiency of computing. And a lot of the current projects aim to do that through specialization. And so when Song started in the group, we tried to look at something that he could specialize in. Because we were part of the platform lab, although it had a different name at that time, we looked at John Osterhout's RAM cloud system. And he probably spent close to the first year of his PhD program trying to figure out how to build specialized hardware for RAM cloud. And I actually think that it would have worked, but we got bogged down in details. I think it was actually an important learning lesson is to not dig into the weeds until you figured out what the forest is that you're dealing with. We then spent time on some other data center applications looking at trying to specialize MapReduce and stuff. And then finally we sort of stumbled onto, I think we actually looked at graphs too at one point. And then we sort of stumbled onto machine learning, and that's when we started making a lot of progress. There had been very little done at that point in time on special purpose hardware for machine learning. It was the opportunity to sort of co-design the algorithm with the hardware. Just building hardware to accelerate the current algorithms wasn't very interesting. People had kind of done that. But by making tweaks to both the data representation and to the problem itself, we're able to make big progress there. And so Song will tell you all about that. And he's passed the test of when a student is ready to graduate. And that it used to be when I would sit down with Song, I would be teaching him. But now when I sit down with Song, he teaches me. And so he's ready to go off and be a professor himself, I guess, at MIT if things turn out.
Yeah. Thanks, Bill. Thanks, Bill, for the kind introduction. And it's 5 great 4 years with Bill. And also thanks for my committee members making the trip from all over Silicon Valley. Thanks for your time being here. So I'm glad to be here talking about the efficient methods and hardware for deep learning today. So as we see, deep neural networks, deep learning, has created a lot of new applications in the past 5 years. For example, self-driving cars, the machine translation, the AlphaGo, or the smart robots. So some trend for such deep neural networks are recently, in order to have a high accuracy and model capacity, the model are getting larger and larger. For example, the ImageNet winner, the size of the winner has increased by 16x from 2012 AlexNet to 2015 the ResNet. And also for speech recognition networks, just within 1 year, the number of training operations increased by an order of magnitude just to decrease the error rate by about only 3%. So you pay a lot of computation just to get 3% decrease of the error. So such large computation, memory reference creates some problems to deploy such deep neural nets really either on data center or mobile phone. There are several challenges. The first challenge is that the large model size make it difficult to distribute. For example, either on the mobile apps, if your app is larger than 100 megabytes, you cannot download until you connect to Wi-Fi. And also for self-driving cars, say you buy a Tesla, and then you want to have those over-the-air updates for the deep neural network models. If the models are huge, it's difficult to download from the LTE. And the second problem is the speed. Training such deep neural nets or run inference on such deep neural nets can be very slow. For example, ResNet 152 using 4 and 40 GPUs when tested at Facebook, it took 1.5 weeks to train and just increased the accuracy by 0.05% compared with ResNet 101. So it greatly limits the productivity for machine learning researchers to prototype and explore new deep neural network architectures. And the third challenge is the energy efficiency. So you know how much, so AlphaGo beating Lossless last year, it took 2,000 CPUs and 300 GPUs. And you know how much electric bill it paid? It's $3,000 electric bill per game. So this greatly limits the deployment, the feasibility of deploying such deep neural nets either on the phone or on the large-scale data centers, because it drains the battery and increases the total cost of ownership on a large-scale data center. And according to Google's TPU paper, if every user using speech recognition in their Google's voice search for only 3 minutes per day, if we're without TPU, Google has to double their data center. So deep neural nets is a very important workload on the data center. So let's see, where exactly does these power or energy consumed on deep neural nets? So here's a closer look. The larger model means more memory reference, which leads to more energy consumption. So this is a table for different operations for under 45 nanometer technology, and we can see that the memory reference is more than 2 or 3 orders of magnitude more expensive than arithmetic. So you do one memory reference, you can do 1,000 multiplication add with the same energy. So it is those memory reference and large model leads to large memory reference that hurts the efficiency of deep neural nets. So how to make it more efficient? I'm proposing to improve the efficiency of deep learning, that is, algorithm and hardware co-design. So previously, when we were designing hardware, we treated the algorithm as a black box, for example, Spec 2006, and then optimize the CPU according to running the benchmarks. So now, what we should do for deep neural nets is to open up the box, see what we can change on the algorithm first, and then optimize the hardware *PU to see what is the best hardware for deep neural nets. So it's breaking the boundary between the algorithm and the hardware. So let's take a brief look into what is in the box. So I'm going to introduce the Deep Learning 101 for some basic concepts for the audience who are not familiar with deep learning. So it is large-scale data set and modern hardware, for example, GPUs, that enable deep learning. So we train the deep neural nets on large-scale data sets, for example, ImageNet, on NVIDIA's most state-of-the-art GPUs, and then we get a model. It could be convolution neural nets, recurrent neural nets, or long short-term memory. And then after we get the model, we give it an input data for testing on those either embedded hardware on the phone or on large-scale data centers with AI on the cloud. So this is the basic setup. So previously, the approach was after you train the model, you obtain the model, and then you directly deploy the model you trained for inference. Since we are using a convex optimization method to cope with such highly non-convex problems, so there's literature saying there's great redundancy in the model you trained in order to have a great local minimum. So what I'm proposing here is to do model compression between training and inference to make the model much smaller, much fewer ops, much fewer memory reference, and then deploy it on specialized hardware. Since compressed model brings irregularities, so there are lots of considerations how to traverse those sparse level of indirection, those irregularities brought by model compression. So the overall goal is to make it faster, power efficient, and doesn't sacrifice the accuracy. So that's my topic today. So the goal for my figure of merits and the goal for this talk will centralize on these 4 factors: smaller model, faster inference, more energy efficient inference and more accurate models. And this is the agenda for today's talk. I'm going to start with model compression by making the model smaller, followed by two hardware accelerators that can run inference directly on the compressed model, followed by efficient training, how to make the model more accurate by such regularization techniques. And I'm going to first start with model compression. So let's first brainstorm a little bit. How can we compress a deep neural net model? So if you think of it, there are roughly two ways. One way, you can reduce the number of connections in deep neural net. Okay? You have 10 million parameters, you can reduce the number of parameters. And secondly, you can reduce the number of bits per weight, so that they multiply together, you get a smaller model overall. So I'm going to first introduce learning both weights and connections for efficient neural network that targets having fewer number of connections and weights. And this is an illustration of pruning your deep neural networks. So originally we have a dense model. Every connections are trained as it is. So pruning a neural network is like pruning a tree where you get rid of those redundant connections. So this has been first explored by Professor Yang Kong back in 1980s. And 26 years later, I revisited this problem given the hardware efficiency perspective and also our modern deep neural nets. So this is how we prune a deep neural network. We train the model as it is before, and then we prune those connections that are redundant based on a very simple heuristic of its absolute value. If the absolute value is small, then set it to 0. And then we don't have to compute. 0 multiplied by anything is 0. So we don't compute, we don't store. Finally, we train the weights, train the remaining weights to recover the accuracy loss brought by pruning, and we can do this process iteratively. And more parameters doesn't necessarily mean more accurate. Sometimes it leads to overfitting. So even sometimes we observe the accuracy improved during this pruning process. And let's see, how does such pruning hurt or doesn't hurt the prediction accuracy? Since every 1% of accuracy counts for deep neural nets. So the x-axis is how much parameter we prune away, say 60%, 90%. And the y-axis is the loss of accuracy incurred by pruning. If we just prune the neural networks naively, we can see the accuracy deteriorates very sharply. At 80%, the loss of accuracy is about 4%. That is intolerable. How can we make it better? We can retrain the remaining weights, the remaining connections, so that we can see the accuracy when we are pruning 80% is the loss is 0% here. It fully recover the accuracy of AlexNet or ImageNet. But if we do this process iteratively, like pruning, retraining, pruning, and retraining, we can push the frontier even further. 90% pruning ratio, no loss of accuracy. So this is on convolution neural nets on image classification. How about there's also other neural networks, such as recurrent neural nets and long short-term memory. How does pruning work on those neural nets? So I experimented with NeuroTalk from Fei's group. It's a baseline model to see if we prune naively, the accuracy drops very quickly for this image caption long short-term memory. But with proper retraining, the green line, the blue score doesn't hurt until you prune away 90% of the parameters. So similar observation for both convolution neural nets and recurrent neural nets in our teams. And here are some visualizations of how pruning long short-term memories affect the caption quality. This is the original image. The caption from NeuroTalk baseline says a basketball player in a white uniform is playing with a ball, versus you get rid of 90% redundant parameters. It says a basketball player in a white uniform is playing with a basketball. Similar for the second image, the baseline NeuroTalk model says a brown dog running through a grassy field versus a brown dog running through a grassy area. But if we prune too aggressively, say 95% of the parameters are removed, the network is going to get drunk. It says, a man in the red shirt and black shirt is running through a field aggressively. So the language model is no longer correct. Okay, so let's see a little bit how does the pruning affect the weight distribution of deep neural nets. So this is the original weight distribution of a deep neural net. And after pruning, the small weights are removed. That's why there's a big gap here. And after retraining the remaining weights, the distribution gets softer. And that's why the accuracy gets fully recovered. So here we can see roughly the weight gets binned into two buckets, right? The positive bucket and negative bucket. So one further thinking is, do we need such continuous distribution? Can we further bin those weights into several buckets? And that's the next idea of trained quantization to further compress deep neural nets. I'm going to introduce deep compression, compressing deep neural networks with pruning, trained quantization, and Huffman coding. And the intuition is very simple. You don't need those high precision weights, say 2.09, 2.12, 1.92, for example. Just quantize them to 2. So the process to do this is by clustering the weights, by k-means clustering, group the similar weights together, and then generate a codebook. Quantize the weights with the codebook so that you only need to store the index, and then retrain the codebook and do this process iteratively. And as a result, you can quantize deep neural nets from 32-bit to only 4-bit. That's 8 times saving in memory footprint. This is an illustration for a 4x4 matrix, a weight matrix 4x4, previously represented with 32-bit floating point numbers. And I'm going to do a k-means clustering to cluster, say, 2.09, 2.12, then you are both 2. And now what you need to store is only the index into this table, which requires only 2 bits in this case, instead of 32-bit. In this case, since we have only 4 centroid. So this is feed forward. How about back propagation? How do we train such weight shared deep neural network? So after we get the gradient, we color them with the same pattern as the weights. And then do a group by operation by having the same gradient with the same color, group them together, sum them up, divided by the numbers, having a reduce operation, and multiplied by the learning rate and subtracted from the initial centroid. And that's one iteration of stochastic gradient descent on such weight shared deep neural network. And let's see, how does weight distribution change? Remember, previously we have a continuous weight distribution. Now, after the weight sharing, we have such discrete weights. For example, in this case, we have only 16 bars, which can be represented by only 4 bits, compared with 32-bit we previously used. And we can, through retraining on those weight shared neural network, you can see there's a subtle change. There's a subtle change of the weights, which compensated for those 1 to 3% loss of accuracy. Okay, now let's see how many bits do we really need to fully recover the accuracy. So I experimented on AlexNet, on ImageNet dataset. So for those conv layers with 6 bits, it's safe to fully preserve the accuracy. And not until 4 bits does the accuracy begin to deteriorate. And for the FC layers, not until 2 bits does the accuracy begin to drop. So far, we have seen 2 methods with pruning and trained quantization. The next question to answer is, do they work well together? So this is figure showing how much can we compress the model versus how much accuracy do we lose. So by combining pruning and quantization, by combining them together, we can make AlexNet 3% of its original size without hurting the accuracy. Well, comparing with pruning and compensation working individually, with 10% of its model size, the accuracy already begins to drop. And also compared with the cheap SVD, factorization-based method, which at 20%, the accuracy already observed, we observed 1% loss of accuracy. Okay, finally, there is a third idea that contributes to the last 30% of saving in the storage, which is Huffman coding. A lossless compression method works on the remaining weights. And the idea is very simple. We can use more number of bits to represent those infrequently appearing weights, and use less number of bits to represent those more frequently appearing weights. This saves another 30% of the storage of the model. So by putting them all together, this is the deep compression pipeline that consists of pruning, less number of weights, trained quantization, less number of bits per weight, and finally, Huffman coding. And the result evaluated on lots of deep neural nets, for example, on Amne's dataset, and also on ImageNet, AlexNet, VGGNet, GoogleNet, ResNet. The compression ratio ranges from 10x to 49x. The accuracy gets fully preserved. And it's not surprising to see that those networks, for example, GoogleNet and ResNet, which have only one fully connected layer, have smaller compression ratio because they are more efficient to begin with, but they can still be compressed by an order of magnitude. Okay, so the next question to answer is, so we are taking an existing model to compress it. Can we make compact models to begin with and then compress it? How does that work? So I collaborated with Berkeley and tested the idea on this thing called the SqueezeNet. It's a very efficient architecture that is only 4.8 megabytes compared with 240 megabytes of AlexNet. Using a squeeze layer to shield the computation expensive 3x3 convolution with less number of channels, to shield it with less number of channels, and then expand it later. So by using such building block, we constructed this large, deep neural network. And actually, the accuracy compared with AlexNet, SqueezeNet is 50x smaller than the baseline AlexNet, but have the same accuracy. So applying compression on SqueezeNet, I obtained a model that's less than half a megabyte. Pretty easy to fit in the L1 cache or L2 cache. So the compression ratio is about 500x smaller than the AlexNet, but with exactly the same prediction accuracy, which shows even those compact model is still amiable to compression. Okay, so smaller model means it's having less memory footprint and more cache friendly. So I tested those fully connected layers, which is simple, on CPU, GPU, and mobile GPUs using the FC layer of AlexNet, VGGNet, and NeuroTalk to see how much speed up do we get from such compression. About 3x saving on the CPU, 3x on the GPU, and about 5x on the speed up on the mobile GPU. And again, for the energy efficiency, it's about 6x battery energy efficiency, 3x on the GPU, and about 4x battery energy efficiency on the mobile GPU for these fully connected benchmarks. So deep compression has been applied in industry, in the apps for Baidu, for example, Baidu Wallet. They don't want to recognize your credit card. They don't want to send your credit card to the cloud. They really want to recognize everything locally. And also Facebook, where I did a targeted internship last year, and also Sogou, the input method company in China, for the data centers. And here is an example of a Facebook AR prototype, which is backed by deep compression, which they are doing image object detection, having their location for either it's a coffee cup, so that it can do their features according to what it is and where it is. And I achieved 8 times model size reduction by deep compression, since Facebook wants to have such fun apps on your local phone instead of having to rely on the network. And it appeared on Facebook Developer Conference 18 here with this demo. Okay, so we have so far introduced the deep compression, which seems a very powerful thing, but it actually creates lots of challenges for hardware design. For example, how do we do those online decompression while running inference, right? And also the computation becomes irregular. We bring sparsity in the weight, and also how to take advantage of sparse activation, how to deal with those indirect lookup. And parallelization also becomes challenging since there's synchronization overhead, load imbalance issue, and scalability issue. So having opened up the box, now we are in this domain to look at the hardware. So what is the right hardware architecture specialized for such compressed deep neural nets? And I'm going to introduce 2 accelerators. We focus on the EIE accelerator. EIE stands for Efficient Inference Engine on Compressed Deep Neural Network. And there are lots of related works for accelerating large-scale neural networks. And they share a common feature, common goal to minimize the memory access, which is expensive. For example, Iris from MIT proposed the row stationary data flow to minimize DRAM traffic. And Dalian from China Academy of Science are using the EDRAM to buffer all the weights on chip. And the recent TPU from Google is using 8-bit integer instead of 32-bit floating point to minimize the DRAM access. And in particular, in the TPU paper, it says that the unit is designed for dense matrices. Sparse architectural support was omitted from time to deploy reasons. Sparsity will have high priority in future designs. And my work, EIE, is the first deep neural network accelerator that supports the sparsity and also its compressed deep neural network. And the design rule is simple. So anything multiplied by 0 is 0. So don't waste the cycle, don't waste the storage. And approximation doesn't have to be exact number. So by taking advantage of the sparsity in the weight, 90% sparsity, there's 10x saving in the computation and 5x less memory footprint. The 2 factor of 2 coming from the index overhead. And also by taking advantage of sparse activation, we save another 3x computation. And by weight sharing using 4 bits to represent each weight, we save 8 times less memory footprint. And the good thing is overall, after compression, the weight can fit in on-chip SRAM, which has much larger bandwidth and much fewer energy compared with having to go to off-chip DRAM. So let's take a look deeper into the EIE. How do we do the parallelization and what is the data flow? So this is a 4x8 matrix in given layer. So we parallelize them by partitioning the matrix into rows. The same color of row goes to the same processor or processing element denoted by TPE here. And in this case, we have 4 processing elements, 4 PEs. And this is how physically we store those compressed weights. Only those non-zero weight, together with the relative index using 4-bit to represent. So 4-bit, that is because 2 to the 4 is 16, which can encode a maximum jump of 16, which aligns very well with the sparsity of about 10%. So in case the jump is more than 16, we apply a padding 0 to compensate for that. Finally, we have a column pointer so that we can know where is the starting address for each column. So this is the data flow for EIE. We have a leading non-zero detection circuit so that we can ignore the 0 activations in the activation and only work on those non-zero activations in the vector. And we broadcast it to the processing elements, to the multiplication, and update the output. Another zero, we ignore it. Another non-zero activation, we broadcast it to the other PEs, and within just a single cycle, we update the output. And in another cycle, we do another set of weights. So after everything is done, we pass it through the ReLU and write it back to the register. So this is the microarchitecture of the processing element of EIE. It's a huge, looks huge, but we can break it down from pipeline stages. First, we have an activation queue to decouple the load imbalance. Say one processing element may have more number of non-zeros, the other may have less number of non-zeros. So we have an activation queue to decouple such local load imbalance. And remember, this is local load imbalance. I'm going to talk about global load imbalance later. And next, we access the SRAM pointer SRAM to know where is the column of the weights. And next, we access the sparse matrix to get the actual non-zero weight in the matrix. So the weight, remember, it's just storing the index. We need to pass it to a weight decoder, which is a lookup table of 16 entries to get the real decoded weight. And for the address, for the index, we pass it through an address accumulator to get the absolute index. And these two elements can be done in parallel. And then we do the arithmetic, multiplication and add, and finally write it back to the register file. Pass it through the ReLU unit and leading non-zero detection unit. That's the whole pipeline of the one EIE PE. And what is special here is this load balance queue to decouple the load imbalance, which increased the utilization from 50% to more than 90%. And also this weight decoder and address accumulator that can be done in parallel to cater for the sparsity and also the level of interaction. So we did the layout, place and route, synthesis and place and route under the TSMC 14 nanometer library. This is the layout of the chip. It can handle maximum number of weights of 84 million. Remember, Alex said it's only 60 million. It contains 64 PEs and the area of 14 millimeters square. And the power is about half a watt or 600 milliwatts. So this is the benchmark. So this is the benchmark I test EIE. So remember here, even before handling it to the hardware, through compression, the number of flops can be reduced by 10x to 100x. 10x because those neural talk doesn't have ReLU, but they use tonnage or signaling. That's why here it's smaller reduction. But it's still 1 or 2 orders of magnitude saving in the number of flops before you handle it to the hardware. So we have seen this figure just now. Now we added another bar, which is EIE. It's 189 times faster on these fully connected layers, compared with CPU, and around 13x faster compared with Maxwell Titan X GPU, and even more faster than the mobile GPU. And energy efficiency-wise, since we saved memory reference a lot, we moved from DRAM to SRAM. So this number is huge saving compared with CPU, about 24,000x compared with the CPU, and about 3,000x compared with the GPU without compression. And if you say it's always the case that ASIC is more efficient than CPU and GPU, so this is a comparison of the throughput with CPU, GPU, and peer ASICs, for example, 大电脑 and True North. So if it's projected to the same technology node, 28 nanometer, EIE is about 1 order of magnitude better than the peer designs. And same for the energy efficiency, both 45 nanometer or 28 nanometer it's an order of magnitude better than the peer ASIC designs. And I eluded this problem of load balancing issue just now. So by having the FIFO decoupling the local load imbalance, I can increase the utilization from about 50% to more than 90% for these benchmarks. Except for this one in NeuroTalk and LCM, the utilization is low, it's about 60%. So the next question to answer is, how do we do better with the load imbalance? And then, how do we generalize from feed-forward neural nets to also support recurrent neural nets? So I'm going to go briefly into the next design, the ESE accelerator, to deal with this problem. And ESE stands for Efficient Speech Recognition Engine for Sparse ILSTM on FPGA. So accelerating LCM, here's some motivation why we need to do this. Because recurrent neural nets are the basic building block for all these applications for speech recognition, image recognition, image caption, machine translation, and visual question answering. And in particular, for speech recognition, if people use Google search for only 3 minutes a day using the speech recognition system, Google would have to double the number of data centers, which means it's a very important application to work with. So we have seen previously, we have compressed the model and then accelerated the model for inference. Now, to deal with the load imbalance, I'm going to rethink the design flow and add this feedback loop to see how can we do better? How can we do better for the compression? And I propose this load balance aware pruning. So what is load balance aware pruning? Before jumping to that, I'm going to introduce where does the load imbalance actually come from. So this is a matrix. So P0 here has 5 non-zero elements, while P3 only have 1 non-zero element. So the total number of cycles is determined by the largest number of non-zero elements, which is 5 cycles in this case for the load imbalance case. But if we enforce such constraint on the pruning process by having the same number of non-zero elements for each PE, then the workload is balanced all 3 cycles. So the overall computation cycle is less than before. And how does this constraint affect the prediction accuracy? So this is how much parameter we can prune away. Originally, 90% no loss, or no increase of the error rate. And compared with the load balance aware pruning, we observed the similar accuracy in this sweet spot, did a lot of experiments locally here. And how about the speed up? Previously, without load balance aware pruning, we get this speed up with the number of non-zeros, about 5.5x speed up, given the sparsity of 90%. Theoretically, there should be 10x, right? 10x, but there's indexing overhead and other scheduling overhead. That's why we observed the 5.5x speed up. But with load balance aware pruning, actually we get 6.2x speed up. It's a free lunch from 5.5x to 6.2x by just enforcing such load balance computation pattern. And I'm going to briefly talk about the high-level hardware architecture of ESE accelerator. It's basically using EIE as building block. Previously, it's sparse matrix vector multiplication. Now it's sparse matrix multiplication. And it has multiple EIEs as a building block. And we also added those element-wise unit. So prototyped on the Xilinx KU60 FPGA, compared with Pascal Titan X, it's taking 82.7 microseconds compared to 240 microseconds by running through a whole long short-term memory with a batch size of 32. Apparently, GPU can handle much larger batch sizes, but given the real-time requirement of QoS, we tested the realistic of 32 batch size of 32. So it's about 3x faster and 14x better energy efficiency. although it's prototype on a badly designed ASIC, which is an FPGA, just to prototype the architecture. Okay, so far, we have seen one challenge is memory access is expensive, right? And I solved the problem by using deep compression, making the model 10 to 49x smaller. But creates another problem, which is sparsity, indirection, and load imbalance. And I solved this problem with two hardware accelerator designs, with energy efficient and also faster. So now let's switch gear a little bit from the hardware back to the training algorithm. Let's switch gear a little bit. And we have so far covered everything in inference. And what about training? Previously, with a compressed model, we can observe the same prediction accuracy, which means can we have higher accuracy for this original model capacity? So for the next 10 minutes, I'm going to introduce the efficient training method by using sparsity as a regularizer. So I'm going to talk about DSD, the sparse dense training for deep neural networks. So now we are back to algorithm part. So we have seen these two figures. By having pruning, we can have the sparse model have the same accuracy as the dense model. The new thing is we can recover those previously pruned weights, showing in red here. Recover those weights and train everything together. Those red weights get a second chance of initialization. They get initialized here, but they got pruned because they are probably not useful in this case, but they got a second chance of initialization and get trained together. And actually have higher prediction accuracy. It's like you learn the trunk first and then gradually add those branches and leaves. So we tested this idea on a wide range of vision tasks, vision networks for GoogleNet, VGGNet, ResNet 18, ResNet 50. For example, the ResNet 50, the error rate, top one error rate, decreased from 24% to 23.2%. And the relative improvement ranges from 3% to 13%. And also I tested on, to make sure it's a general purpose method, not only works on convolution neural nets, but also recurrent neural nets, RSTMs, for vision, speech, and natural language. I also tested on NeuroTalk, increased the BLUE score by 1.7, and also collaborated with Baidu to test how it works on deep speech neural nets. Again, the accuracy, relative accuracy improved by 5 to 7%. So here are some related work like JobPod and JobConnect. They use random prune or the zero away random weights rather than DSD training. We are zeroing away those small weights deterministically. And also distillation, model distillation is also trying to have a student model to learn from the teacher model and have a smaller model have better accuracy. And both DSD and distillation doesn't incur any change in the architecture. And it's interesting to see how if we combine these two methods together. As a summary, so far we have visited three main points in the presentation about model compression to compress the model, make it smaller, less flops, less memory footprint, and then hardware acceleration. Discussed the two hardware accelerators, EIE and ESE, and followed by another idea for efficient training using sparsity as a regularizer to have better prediction accuracy. So to project my project into this matrix of inference on the left and training on the right, algorithm and hardware, I'm using sparsity to make the model smaller by deep compression, and better speed and energy efficiency on the hardware inference side to make it with EIE and ESE accelerator. And the training and algorithm side is ESE regularization targeting higher prediction accuracy. And training hardware remains to be the future work. So in summary, such efficient methods and techniques will be helpful for deploying deep neural nets or giving those devices intelligence either on the phones the drones, the robots, self-driving cars, and also enable making it more efficient to run AI in the cloud as well. And if you see this future, our city will be populated with lots of smart applications, for example, smart cars, smart building, smart retailing, and big data. So hardware will be an enabling factor for such revolution, which requires smart, low latency hardware, user privacy, good mobility, and good energy efficiency. So outlook into the future of computation, we have moved from the PC era to the mobile era. Now we are in the AI first era. And hope you are excited as me for this kind of brain-inspired cognitive computing research. And finally, many thanks to my advisors and collaborators and my friends. And in particular, I would thank Bill for the entire 5 years of advising me. I learned a lot from Bill. For example, finding a problem is equally important as solving a problem. During my first 2 years, finding the problem I'm going to do here took me a lot of time, which usually the high impact work usually comes from a good direction and solving a real world big problem. So in the future, and also remember last year, it was a conversation with Bill in GTC that ignited me in the academia for my career. And it turned out to be successful, and I'm very thankful for Bill pointing me to this direction. And also I'm thankful for Mark. I remember we first met in 2001. Before I joined Stanford as an undergrad, you were the department chair, and you encouraged me to apply for Stanford and lead me into this beautiful campus. And following years, we have lots of discussions. Give me, whenever I was deviating from the road, you put me back. In particular, this deep compression work for initialization pointing me, you should try to, I was having difficulty closing the gap of the accuracy for those last 1%, and important me to look at minimum and maximum initialization rather than those random initialization. And those careful thoughts really paid off for better projects and more editing all the papers and all the work. And I'm also thankful for Fei. Actually, I took your class in computer vision and later the deep learning class also with Audrey Kapati that set me very brand new direction looking into deep neural nets, the marriage of deep neural nets with hardware. You mentioned marriage of machine learning with computer vision, but now it's the marriage of deep learning with hardware, which make a big impact on my research path. And also remember last August, a conversation at your office also encouraged me a lot to continue apply for faculty position and its academic path. So thank you for all these encouragements and advice, and adopted me in your group partially. Also thankful for Crystal. It's been a long time taking your class, or the computer architecture class, and also interacting with your students, and Mingyu and Grant and Daniel Sanchez bring me in the domain of computer architectures and lots of advice and help for my research. Thanks for joining, taking the time to be flexible for scheduling my defense and being flexible. And thanks for all my friends for the support and encouragement throughout my PhD path. I'm incredibly grateful for those who have supported me along the long journey. Finally, my thanks to my mom and dad. They are not here today, but they were the first community that encouraged me to find my passion in the research. So thank you. I spent 5 years very happy life for my PhD with the CVA lab and those academic activities, and also those fun activities, TAing the course, going skiing and bicycling. Partially those hobbies are inspired by Bell and also rock band. Thank you all for my friends and my advisors. Thank you for your coming today.
little bit of time for questions during the open session of the fence before we go to the closed session.
For training for sparsity, in the past I've noticed people doing L1 regularization. How would that relate to what you've done?
Yeah, so that's a good question. I have a backup slide for that. To simplify the discussion, I omitted that part, but it's a good question put in the paper. So this is showing the using L1 regularization versus L2 regularization. So the observation, this is a dashed line for forward training. L1 regularization performs better. So 80% leads to less loss of accuracy compared to L2 regularization. But after retraining, it turned out L2 regularization actually gets better result compared with L1 regularization. So I used L2 regularization throughout the work.
I have a maybe silly question on hardware. So do you think clock gating is feasible for the neural network? Do you consider the conversion speed for every part of the network?
The question is clock gating on.
Do you think clock gating is a good way to improve the energy efficiency of the neural network?
Yeah, there's been work on clock gating. For example, the Iris chip from MIT. They can, whenever it observes the zero multiplied by anything is still 0. So they don't waste the energy to do that multiplication, but they still use the cycle. So it saves the energy. But doesn't save the computation cycle. But it still buys you the energy. Yes.
Any more questions?
Just one more question. For the energy efficiency, the percentage improvement, what's the metric for efficiency that you're using?
So efficiency means the speed and also the energy it takes to run the inference.
And when you say 16x or 100x, what is it compared? Like, is it joules per flop or something like that?
Oh, so it's joules per layer. How much joules do you need to run this neural network? And also the latency, like how many microseconds it takes to run this layer. Yeah. So one is energy, the other is latency.
So you implemented this in a FPGA.
Right.
Is that the best architecture, or is it just for prototyping?
It's just for prototyping. Actually, there are some limitations for the FPGA. For example, it has only 4 megabytes of on-chip memory. But if I were to give it about, say, 10 megabytes, I can easily buffer everything on-chip. And also, the utilization is pretty low, given there are 2,000 DSPs, and it turned out only 1,000 is used. So there's a lot of imbalance limitations for FPGA. But it's cheap to prototype. That's why in academia it's a good thing to use. But in production, it remains to be seen.
So the training in low precision is hard, but do you think it is because like the training absolutely requires that much higher precision, or like people hadn't figured out a way to train in low precision?
Oh, that's a good question. I have another backup slide for that. Actually, from the CS231 lecture last week, I prepared this slide from the most recent NVIDIA's mixed precision training, which can train deep neural nets using 16-bit floating point. Let me put it out very quickly. Sorry, it's 100 slide, so it's slow to put it out. So this is from NVIDIA GTC just 1 month ago. And it's possible to do train neural networks by feeding forward with floating point numbers 15 at P16, and also back propagate with that P16, and also the gradient. The new thing is when we do the weight update using full precision 32-bit floating point to do the update. So this is using the mixed precision training, and it turned out for inception model, the accuracy convergence is pretty similar between that P632 and this mixed precision training. And also, for example, ResNet, the convergence is pretty much the similar. And the final result, P32 versus the mixed precision training differed by a little bit, for the final converged speed. But using 16-bit rather than 32-bit saves about 4x area and also the energy. So that's possible.
Is it even possible to go into even lower precision?
Oh yeah, another backup slide. So yeah, last quarter, I mentored Chen Zhuo to try this idea of using ternary neural nets with only 3 weights: a positive weight, 0, and a negative weight. So it turned out we can have, this is validation accuracy. This dash line is the baseline. We can achieve the same error rate compared with the full precision neural net by having only these three weights: positive, 0, and negative weight.
Okay, so let's call a close to the open session. Thanks everybody for coming. Let's take a 5-minute break and reconvene at 2 o'clock for the closed session.